Guys, don't forget to join the Pomboloka team and secure a future academia at the University of Zambia.
And remember, Nala Pomboloka, Wala Pomboloka, Twala Pomboloka. Pomboloka!
Alright, welcome to this particular part of the video where we want to focus much more on how the rate of a chemical reaction can be affected by temperature. You will basically understand that the previous lab that you are doing, you're looking at how the concentration can affect the rate of a chemical reaction, but now we want to put much more emphasis on how the rate of a chemical reaction can be affected by the use of that particular temperature. So we want to look at the technicalities of procedure. And I should also mention that we are going to be given two reacting vessels, the two most important reactants in this particular chemical reaction. And those reactants are the sodium thiosulfate, and we're also going to be given the sulfuric acid of different volumes. And then aside that, I also want us to take note that we've been given a table which has not been depicted in your lab manual, but it is very important that you know an exact way on how you're supposed to draw this table. It is going to have different type of quantities. The first particular quantity is going to have is called the temperature, and then we have the time, and then we have the in of time, and then we're also going to have the reciprocal of the time here, which is just 1 over the temperature. And I should also mention that this temperature here is going to be in what? It is going to be in Kelvin. All right? Now, the initial values of the temperature you're going to get when you're given that thermometer is going to be in degrees Celsius. So I should also mention that the SI units for this particular kind of a lab is very important. And then you have to convert those SI units. If you're given, for example, the temperature in degrees Celsius, you're supposed to convert that temperature to Kelvin. And how do we do that? We know that when you're converting that, that becomes Kelvin, which is equal to the degrees Celsius plus 273.15 K. So now, like I mentioned in the introduction of this video, we're going to be given the sodium thiosulfate as one of the reactive vessels. And then the sodium thiosulfate has been given as a volume of 10 cubic centimeters. So we're going to get, first of all, the temperature or the room, the RTP temperature of this sodium thiosulfate, which is at 10 cubic centimeters. So for example, when you come to the video here, or to the table, you're having 20 degrees Celsius as the temperature that you've taken out for the sodium thiosulfate. And after taking out of that temperature here, you would want to mix that sodium thiosulfate with the sulfuric acid. And the volume of the sulfuric acid is 1 cubic centimeters. So what have I done here? What are one of the most important details I've taken? I'm saying I did find out the RTP temperature here of the sodium thiosulfate as 20 degrees in a volume of 10 cubic centimeters. And then I'm going to collect 1 cubic centimeter of the sulfuric acid, and I'm going to put them all together. Now, there's something very important and significant that you should know before you mix them. When you get the sodium thiosulfate, and you also get the sulfuric acid, at the point where you start mixing them, you need to start the reaction time. And the moment you see a cloud mixture or a precipitant in that particular test tube, you're going to stop the time. So initially, the temperature was at 20 degrees Celsius. And then we want to move from 20 degrees Celsius, we want to move to 25 degrees Celsius. But the question here is, how do you move the temperature of the sodium thiosulfate from 20 degrees to 25 degrees Celsius? We're going to be given a beaker of boiling water. And then we're going to get the sodium thiosulfate with the thermometer inside. We know to say, okay, we're at 20 degrees. We're at 20 degrees. We want to move from 20 degrees going to 25 degrees. So now, because there's that beaker of hot boiling water there, I am going to get the sodium thiosulfate with the thermometer inside, going to place it in the beaker that has hot boiling water. And when I do that, I'll start taking note of the temperature changes. If I go up to 25 degrees Celsius, which is right here, if I go up to 25 degrees Celsius, I'll stop. And then I'll go and collect the 1 cubic centimeters of the sulfuric acid And then I'm going to mix them all together and also take note of the reaction time. So initially, the reaction time for the first experiment that we did was 50 seconds. Then the second time is now 49 seconds. So what does this mean? It means that initially when we had a temperature of 20 degrees, the time was 50 seconds. We now have a temperature of 25 degrees, we're at 49 seconds. So the more you get to increase the temperature of this reaction, what is happening is that the reaction time is decreasing. So when you come to 30 degrees, you come at 35 degrees. You come at 35 degrees, you come at 23 degrees. Or we come at 23 seconds. So what is the basic emphasis here? What is the whole logical metamorphosis of what we're trying to do here? We're trying to simply understand the fact that when you increase the temperature of a chemical reaction, you speed up the rate of that chemical reaction. So now, we're moving in an interval of 5 degrees. We're moving in an interval of 5 degrees Celsius. So from 5, we've gone to 25. From 25, we've gone to 30. And basically, this is how you work out the entire table. So when you come here, you're simply going to be taking note of the time. So the in of 50, you fill up the entire table. And then this is 1 over the temperature. This is not 1 over the time, but this is 1 over the temperature. And I did emphasize that the temperature should be in Kelvin. So you won't be getting the temperature that is in degrees Celsius. But what you'll simply be doing is getting the temperature that is in kelvins. So now, the reaction has been depicted here. And then you also come here. This is just the rate law of this chemical reaction. You have the concentrations of the acid, and then you also have the concentrations of the sodium thiosulfate. So now, out of the entire thing, we also want to come up with a graph. How do we depict the graph that is going to show how the rate of a chemical reaction is affected by temperature? With me, we've got Mr. Chola going to tell us the entire way and how you come up with this important equation which has been given in the lab manual. Let's see.
All right. So we now move into another part. We have been asked to plot a graph of the negative log of time against the inverse of the temperature. But how are we really going to understand this so that we are able to comprehend the effect of temperature on the rate of chemical reactions? So in our reaction, we have thiosulfate reacting with sulfuric acid, and it is producing a precipitate, in this case, sulfur. So sulfur is what is enabling us to know the end of the reaction or the production of the products. So if we want to determine the rate of a chemical reaction, we can either observe the disappearance of the reactants or we can observe the appearance of the products. So this is what you can see here. Either the disappearance, so that we're having a negative for the concentration of hydrogen and thiosulfate, or the appearance of the products, in this case, sulfur. So if we write the rate law of our chemical equation in relation or relating to the reactants, we're going to have R for the rate of the chemical reaction being equal to the constant. Then we have the concentration of the hydrogen ions and the thiosulfate. So let's term this to be our equation 3, numbering this as 1 and this other one here as 2. So how much of, let's say we consider producing the same amount of sulfur at different temperatures. How would that really affect us? So this equation is telling us if we produce the same amount of sulfur at different temperatures, how would that change? So we have this equation. This is the concentration of sulfur, which is being constant, yet the temperature is changing. So we expect if we're to produce the same amount of sulfur at different temperatures, we expect them not to be, the time difference to be there. So in this case, we have this equation that is substituted into equation 3. So where we have the rate, we have substituted this part in this one. So as you can see here in equation number 5, we are now introducing the natural log on both sides. So upon introduction of the natural log on both sides, we are able to simplify this equation until we get equation 6. So this is what we have for equation 6. And later on, as we know, when it comes to chemical kinetics, it all goes by the collision theory. And Arrhenius' equation over here as equation 7 explains to us how these chemicals or reactants are able to collide and produce the products. So the Arrhenius equation is given by K, which is the constant, being equal to A raised to the power of the negative EA over RT. A being the pre-exponential factor and EA being our activation energy. So we are also going to do the same by adding the natural log on both sides. So we're going to have equation 8. So there is a similarity between equation 8 and equation 6 because they all have this part, which is the natural log of K. So we are going to substitute equation 8 into equation 6. And upon substitution, what we have is equation 9. It is quite a long equation, but we are able to consolidate it or to simplify it into this equation, which is equation 10, which has the negative log of t, which is time in seconds, being equal to the negative of the activation energy over the gas law constant and multiplied by the temperature. This entire part for the reactants, the concentrations is considered to be a constant plus C. So if you look carefully on this equation, we find that this equation is in the form of y is equal to mx plus c. That implies once you are to plot a graph of y against x, which is the natural log, the negative natural log of our time against the inverse of our temperature, we are able to get a straight line with a slope of negative activation energy over the gas constant. So once you plot, your y-axis will have the negative, the natural log of time in seconds, and the inverse of temperature on your x-axis. Remember, just as you had collected, the units for time is in Kelvin, so as the units for the temperature rather is in Kelvin, and that of the time is in seconds. So once you plot, you're expecting to have a negative slope, and that negative slope will be correlated to our gradient for us to find any other values that will be asked henceforth. So this is quite a very good reaction, and we can tell as we go through how temperature is able to affect the rate of chemical reaction. Even if you are given a given temperature, using the graph, you are able to extrapolate from your graph and get the time it would take for such a chemical reaction to occur. So this is what we're doing in this lab experiment. Thank you.
All right, so we now want to move into the technicalities of procedure. We want to see what exactly are we talking about in our theory, and the practical part of it, we do appreciate it a lot because it is able to give us the entire brief metamorphosis of what is happening here. So you can see right now that we are having the two reacting agents, and the ones that we had was the acid, and then we also had the sodium thiosulfate, right? Yes, so the sodium thiosulfate has already been measured, and we said the volume of the sodium thiosulfate was 10 cubic centimeters or 10 mils, and then the volume of the sulfuric acid was 1 cubic centimeters. So what are we simply doing here? We're trying to mix the first test tube into the second test tube. And immediately the first test tube, that is the second test tube, or the reaction is starting. At the moment at which the reaction is starting, we are going to start the timer and find out what time it is and stop the timer at the moment when we see the precipitant forming or when we see the cloud mixture that is happening. So with Mr. Shola here, we are going to make sure at least we start the timer.
All right, so thank you very much. And so we've already measured 10 mils of sodium thiosulfate and a mil for sulfuric acid. So, but before we can mix the two, we want to know the room temperature of our sodium thiosulfate. So we get our thermometer and place it in, shake it up a bit. So this shows this is right about 17 degrees. 17 degrees Celsius. So we're going to take note of that temperature in our table. That is for test tube 1 running at 17 degrees Celsius. And we're now going to mix the two test tubes. So as soon as the two reactants are mixed, the time will start. Are you ready?
Yes, I am.
Okay, so here we go. Now we wait to observe for the precipitate to form. And as soon as it forms, we end our time. Nothing yet. Our reaction mixture is still clear. I think I'm seeing something.
Okay.
Okay.
It's starting to form.
It's starting to form, exactly. All right, we can stop the time now. Okay, so as soon as you observe a change in color, when it turns to a cloudy mixture, that implies that our precipitate is being formed and hence we stop the time. So this is where we stop.
All right, thank you so much for that. So, what are we supposed to observe in here? If we get back to our introduction, you remember that we needed the sulfur as one of the major products in that chemical reaction between the sodium thiosulfate as well as the sulfuric acid. And that is the more reason why we're able to see this cloud precipitate. So, now you should also remember that we're varying the temperatures in the table that we had, right?
Yeah, yes, exactly.
Because we were starting with 20 degrees, and after measuring here, because we're doing the practical part of it, we have started at 18 degrees Celsius, right?
17.
17 degrees Celsius. So now we're trying to move from that 17 within an interval of 5 degrees Celsius. So from the 17 in the first test tube, 17 plus 5,
22.
that is 22 degrees Celsius. So now how do we increase the temperature from 17 degrees Celsius to 22 degrees Celsius? I did mention that we had a beaker full of boiling water, and we're going to use that beaker to increase the temperature of the sodium thiosulfate. So the initial temperature that is here is at 17, yeah?
Yes,
Is at 17 degrees Celsius. So we're going to move this to 17 to 22 degrees Celsius because we've already added the 5, right? Exactly. So let's see how that works out in the second part of the reaction. All right, so we've done the first part of the experiment at a temperature of 17 degrees. Then I did mention that from that 17 degrees, we're trying to increase the temperature. We go as far as 22 degrees because we're trying to move in an interval of 5 degrees Celsius. So from 17, how do we increase the temperature? I did mention that we have a test tube here, a very beautiful test tube full of water that is boiling. So you can check that in the thermometer here, we have the temperature at 17 degrees Celsius. So what we have in here is called the sodium thiosulfate, and I'll make sure once I put it there, what is going to happen there is I'm going to expect a change in the temperature, and I want it to go as far as 22 degrees Celsius, 20, 21, 22. All right, there we go. Okay, there we go. So the temperature reading is very sensitive. So if you can see there, we've gone as far as 22, that is from 20, 21, 22. Okay, so it's still moving up. So when you have such kind of mistakes, this is not really a mistake, but when you have such kind of a temperature that is a thermometer that is very active, we did collect some water in a test tube, which is called water. we're going to reduce the temperature until we maintain at 22 degrees Celsius. So the main target is making sure we only have 22 degrees Celsius. And it's still moving there. 20, 21, 22. All right, I'm there. So it has now gone back to 22 degrees Celsius. And then from this point, we're going to mix with the 1 ml of the sulfuric acid.
So right about now, after getting the appropriate temperature from the hot beaker there, we're now adding the sulfuric acid. So the time, could you kindly help me note the time? As soon as we mix the two. So,
Okay.
so now let us observe and wait for our precipitate to form. So we have to really look closely because the very first signs of our precipitate, that's where we stop our timer. Okay. Still so clear? All right.
Right.
So we can stop our timer. Yes. So as you can see, there's a cloudy mist formed inside the reaction and it's getting intense. But in our reaction, we are only expecting to stop our timer at the first moment we see the cloudy color being formed within the reaction. So that is the precipitate, which is sulfur, that is being formed in our reaction vessel in this test tube. Thank you very much. To you, Mr. Pombo.
So basically, this is how we are carrying out the whole entire experiment. And with my entire team here, Mr. Shola, and then also with one of our colleagues here, this is how you carry out the experiment. And this is a clear demonstration of how temperature can affect the rate of a chemical reaction. So I think now you should know that when I increase the temperature of the reactive vessels, I expect the rate of a chemical reaction to do what? To increase. So basically, thank you so much for watching. And remember to subscribe to the channel and also join us in the Pomoroka movement as we secure the future of academia at the University of Zambia. Thank you so much.
Viva Student Power, viva! Viva! Viva Mamuma, viva! Viva! Viva Mamuma, viva! Viva! Nada Pomoroka, wala Pomoroka, wala Pomoroka, Pomoroka!
Nala pomboloka. Nala pomboloka. Nala pomboloka. Nala pomboloka. Nala pomboloka. Nala pomboloka. Nala pomboloka.
Nada Pomoroka.